my vertical and horizontal component, and my vertical component will be for velocity, and my horizontal component will be for time. That's the kind of graph that I'm willing to plot. So which implies that I should get my parameters in terms of time and velocity. At each point, at each stages of motion, I need time and the corresponding velocity at that time. So these are the things that I will really need. But I've already analyzed one. We said the body starts from rest, which means that if the body is starting from rest, then when t is equal to 0, permit me to rub this off and start writing. So when t is equal to 0, my initial velocity u equals to 0. That's one. And I've also gotten that when t becomes 30 seconds, when we go to 30 seconds, my velocity at that point is 240 meters per second. So I will write those things out now. So at t equals 0, v equals 0 as well. When we have 0 seconds, t equals to 0 meter per second. We've also calculated that when t got to 30 seconds, we have what? Our v was 240 meter per second. Now, before I proceed to the next stage of the question, if you notice very well, the time is increasing from 0 seconds to 30 seconds. Although time can never be paused, you can never have 0 seconds. But because of the frame of reference that I talked about the other time, that is, there's always a frame of reference. So a frame of reference is where you are starting from, where you are coming from if you are going to a place. So from that frame of reference, then you can always say that as at that time, your time is 0 relative to the frame of reference. That means that you've not started the journey. So your time has not started counting. It's just like you bought an airtime. Now, if your time has not started counting, you have to use 0 time on the thing. So time cannot be 0, but according to the frame of reference we are starting from, our time is 0 seconds, but the time is increasing. So when the time increases to 30 seconds, the velocity increased to 240 meters per second. So what has happened here is actually what? Acceleration. But if you continue the question said a body at rest was given an initial uniform acceleration of 8 meters per second squared for 30 seconds, after which the acceleration was reduced. This is telling you something. It said acceleration was reduced. Remember I said the other time that whenever you have reduction, decrement in acceleration, this type of acceleration is known as deceleration or retardation. So which means that what will happen, definitely what will happen is that as the time increases, the velocity will drop. Because I already said that acceleration deals with increment in velocity with respect to time. But deceleration deals with what? Decrement in velocity with time. So let's see how that works. Let's see how it works. Now, again, deceleration is like the negative of acceleration. I said it the other time, like if you are doing your word and opposite, if acceleration is a word, then the opposite will be what? Deceleration. So if we represent that mathematically, let me just put that here. Acceleration. If D represents deceleration, let me represent. If D represents deceleration, if D represents deceleration, then that means that D equals minus A. So let's take note of that. Now, because for this next stage of the journey, after which the acceleration was reduced to 5 meters per second squared, it's a deceleration. So still using so we now have new parameters. So permit me to use this side of the board. I'll be writing whatever I get here. So permit me to use this side of the board for the calculation. So I was given, so the time was 30 seconds then. Now, the initial velocity now, like I said now, the journey is being continued. So the initial velocity here will be the final velocity for the last stage of the journey. So the new initial velocity for this next stage of the journey will be 240 meters per second. That's one. And the acceleration has been reduced to 5 meters per second squared because it's a reduction. So in that case, my acceleration is going to take a negative value. A will be minus 5 meters per second squared. Why? Because the acceleration was reduced. Now, again, we're given the time that it was reduced, after which the acceleration was reduced. to 5 meters per second square for the next 20 seconds. Look at that statement, for the next. That means that they did not start taking another frame of reference according to the question. So you still continue from this 30, which means that after 20 seconds my time would have become how many seconds? That would be 50 seconds. Now this implies, so let's now look for what the velocity would have become at that time. So using this same equation, we have v equals to u plus at. So we have v now equals, what's our u? Our u is 240. Then plus, what's my a now? My a is minus 5, and the time taken is actually 20 seconds, because that deceleration happened within 20 seconds. So times 20. So I will have my v equals 240 plus minus 5 times 20, that will give me minus 100, and I will have here 240. Of course, plus times minus, we know that from basic mathematics that will give you negative, so that will be minus 100. So my v will be 140. Now do you see that now? You see what has happened here is that my final velocity for this next stage of the journey has reduced. Why? Because it's the case of deceleration. It deals with decrement in velocity. So I have my velocity that corresponds to this point to be 140 meter per second. Now somebody might ask, why am I doing all this? Why am I writing the corresponding velocity at a particular time, the corresponding velocity at a particular time? Why? Reason is because there's this notion that has always been created in our head, that whenever you are asked a question about velocity time graph basically they always form a trapezium. I believe everybody will be able to relate with this. You're familiar with the fact that any velocity time graph, you just have this, you have this, you have this. A trapezium. But this is very, very wrong, a wrong notion to be corrected. Not all velocity time graphs give you a trapezium. It depends on the path of the motion that the motion wants to take. So by actually doing all this and plotting a graph with these points, you will be able to get the exact velocity time graph that is required of you. Let's continue with this question. We'll see what I'm talking about. Now, furthermore, the body maintains the speed attained for 60 seconds. The body maintains the speed attained. That is, the body decided that, okay, I don't want to increase my velocity now. I don't want to decrease my velocity now. Now let me post a question which I will answer myself, of course. This is a video. If you don't increase velocity, don't forget acceleration is change in velocity, because before acceleration can happen, there must be a change in velocity. Now, if acceleration is now either increment or decrement, which will give deceleration, what happens in a case whereby I do not increase the velocity and I don't decrease the velocity? Then automatically in that point I will have no acceleration. That means that there is a case of movement without acceleration. Is that not wonderful? That is, you can actually move without accelerating. That implies that if you move in such a way that you did not change your velocity over a time interval, then there will be no acceleration at all. So that's what exactly happened here. You have observed this while somebody is driving. If somebody wants to increase the rate at which it is moving, the person will have to increase the velocity, a driver. But at a point in time, the driver might just want to cruise along. Permit me to use that one. As he's driving, the velocity is not changing, the driver is just cruising along the road. So at that point in time, the driver is not accelerating. So this is what is happening here. The body maintains the speed attained for 60 seconds. What was the speed attained? Our 140 meters per second. So we don't need to do any bogus calculation here. All we have to do is that for another 60 seconds, then our time would have become, that would be 50 plus 60. So we have 110 seconds. Then our velocity at that point in time will still remain 140 meters per second, because the velocity did not actually change. And don't forget I said, so definitely from 50 seconds to 110 seconds, there was no acceleration because the velocity was constant, was uniform. Now, let's proceed. After which it was brought to rest in 20 seconds. And this, after it maintained this velocity for that 60 seconds, it now said, oh, this journey should be concluded. So for the next 20 seconds, of course, in the next 20 seconds, the time would have become 130 seconds. So after that time, the body was brought to rest. Now, that time is coming up again, brought to rest. So I believe everybody watching this video should be able to conclude that the velocity at this point of rest will be 0 meter per second. Now, having all this, I will be able to plot a glorious, permit me to use that word, a glorious velocity time graph without any hiccup. So let's try and see that. I will rub this part of the board off so that I can write these things there as a form of coordinates, and I will use this place to plot my velocity time graph. So for the first stage of the journey, permit me to write it in this form, t, v. So for the first stage, I have 0, 0. For the second stage, I have 30, 240. For the next stage, I have 50, 140. Now, for the next stage, I have 110, 140 again. And for the last stage, I have 130, 0. Now that I have my coordinates written here, so all I just need to do is plot my velocity time graph now. To plot my velocity time graph. Now, so having gotten our coordinates here, the time and the velocity, 0, 0, 30, 240, running to 130, 0. Now, we need to plot our velocity time graph. Like I sketched the other time, we have our velocity on the y-axis, which is in meter per second. Our velocity is on the y-axis, and we have the time, which is in seconds, on the x-axis. This is the horizontal axis, also known as the x-axis, and this is the vertical axis, also generally known as the y-axis. So we have the velocity there, we have time there, and don't forget the question required us to solve, to sketch a velocity time graph. Mind you, it's a sketch, it's not a plot, so there might be some irregularities there, so please don't mind. Now, so let's locate all these points on our velocity time graph. We have 0, the time is ranging from 0 to 30, 30 to 50, 50 to 110, and 110 to 130. So let's randomly locate this time on the time axis. So we have the 0 here. The 0 will work for both the velocity and time. Now we have 30. The next stage we have 50. We have 110. We have 130. And for our velocity, we only have 240 and 140. So every other value there is 0. We have 0. To let our 140 be somewhere around here, and let the 240 be somewhere around here. Now, so the first stage of the motion, we have 0, 0. So let's locate a point here, 0, 0. When time is 30, the velocity is 240. So let's trace 30 seconds to 240. We have this. So let's locate the point here. This is one of the points that our graph will pass through. Now, when the time is 50, we have the velocity to be 140 meters per second. So this is 140 meters per second. I have this. So we have another point here. And same thing when the time is 110, the velocity still remains 140 meters per second. So this goes up here and still 140. So we have another point here. And the last point, which is when time is 130, we have velocity to be 0 meters per second. So we have another point located here. So the next thing to get our velocity time graph is to connect the points that we have gotten. So connecting the points, we have a movement from here straight. That's the point of acceleration, and as you can see, this falls, which is the point of deceleration, and this is a point where we have a straight line. This shows that we have no acceleration. It's a uniform velocity, and the last stage of the motion is a deceleration. This gives our velocity time graph. Now let me clean these dotted lines so that we can view our velocity time graph very well. I will still need the dotted lines later on. So this is our velocity time graph. Like I said the other time, the common notion that most physics students have about velocity time graph is that it will always look like a trapezium. But no, I said it the other time that not all velocity time graphs look like a trapezium. As you can see in this case, this shape is not the shape of a trapezium, even though there is a section of it that is looking like a trapezium. But the entire shape is not a trapezium. So this is why whenever we want to plot a velocity time graph, we don't just assume it to be a trapezium. We need to get the coordinates of the motion out and locate each coordinate, thereby plotting the graph after. So let's proceed to the next stage of the question. The next stage of the question is to find the maximum speed. Don't forget I said if we are taking into consideration uniformly accelerated motion, if I say speed, I also mean velocity. I've explained that already. And if I say displacement, I also mean distance. Even though these two things does not mean the same thing, but for uniformly accelerated motion, they tend to be the same thing. Now, so if I'm looking for my maximum speed here, come to the scale where we have the speed. You don't really need to calculate that. This is where we have the speed. If you look at the maximum place attained here, it's at this point. If you trace that to the velocity axis, we have the velocity to be 240 meters per second. So definitely that solves that problem, that the maximum velocity or the maximum speed attained, the maximum speed is 240 meters per second. So that's that. We don't need to dwell much on that. Now, the next one wants me to find the average retardation as the body is being brought to rest. Average retardation. Now let's take the stages of the motion into consideration. We have like how many stages here? Let's count. The body moves from here to here. That's the first stage. The body moves from here to here. That's the second stage of the motion. That's 2. We have another stage here. That's 3. And this last stage, which makes us have 4 stages of motion. Now let's analyze what happened in these different 4 stages. We have, from the first stage, we have an acceleration. The second stage is the case of deceleration. The body decelerated. And the next stage, which is the third stage, we have the case of uniform velocity, and this the instance of no acceleration. And when it's the last stage, we have deceleration. But this question wants us to find the average retardation as the body is being brought to rest. So which implies that the stage of motion that we are concerned with here is the last stage of the motion, because the last stage of the motion is when the body is being brought to rest, which is the fourth stage. So for now, I don't have to concern myself with this part. I only need this part. This is supposed to fall directly on 110. So I'm only concerned about this part. Now I need the retardation, and I said in the other time that retardation is also known as deceleration. Now if it is deceleration has something to do with acceleration. I said that it's like word and opposite. If you have acceleration as a word, then the opposite will be deceleration. And mathematically it can be expressed as deceleration equals minus a. All these things I've said it before, I'm just recapping them. Now in this case we have something. If you analyze this last stage of the motion, we have the time interval. These are the things that we need to solve questions. Because we are looking for the retardation, we might actually need the velocity, we might need the time. So to get in order to get the acceleration, we might even need the displacement. But let's see which one we have here already. Now from this place to this place, which is the last stage of the motion, like let me label it. This is the first stage. This is the second stage. This is the third stage, and this is the last stage, which is the fourth stage. So from this fourth stage, it ranges from 110 seconds to 130 seconds. So which means that for that last stage, for the last stage of the motion, the time is from 110 to 130, that's 20 seconds. Time is 20 seconds. And the initial velocity, because the last stage of the motion started here and ended here. So if you trace this to the velocity part, so the initial velocity, like I said the other time, that it is where you are starting from that you take your initial velocity. So if the last stage of the motion is starting from here, then the initial velocity is this, which is 140 meter per second. So u equals 140 meter per second. And if you look at the final stage, like the final part of the motion in the last stage, that's what the velocity there, which is the final velocity, is 0 meter per second. So we have our v to be 0 meter per second. And I think from what we have done earlier, we don't need any other thing again to get our deceleration, since deceleration is an acceleration, just that a negative acceleration. And we will actually confirm here whether what we have been saying about deceleration being the negative of acceleration is actually true. Obviously, from this graph, you can see that this fourth stage is a case of deceleration. Now, we have the time given, we have the initial velocity, we have the final velocity. We are looking for the acceleration. So, quoting the formula that we've been using from onset, our v equals u plus at. Now, let's insert everything we have. Our v is 0, u is 140, then plus a we don't know, so we have our a here, then multiply by, what's the time? The time is 20. Doing this, we have 0 equals 140, then I will have plus 20a. Now you would permit me, because I don't need this coordinate again, I've already plotted the graph, so permit me to rub up the coordinates. Now, so I'm moving this calculation up here. So here, we take 140 to the other side, so it's become minus 140 equals 20a. And what do I do to get the value of a here? I'll divide both sides of the equation by 20. So dividing both sides of the equation by 20, mind you, it's a theoretical question. If you are doing a theoretical exam, a written exam, what I just said now, by dividing both sides by 20, you have to write that down so that the marker can know what you are thinking in your mind. But if it's an OBJ question, you can skip the writing. Now, so if you divide this, definitely you have minus 7, and the unit is meter per second squared, which is the acceleration. Now, this is establishing what I've said earlier, that in a case whereby you have deceleration, the acceleration will take a negative value. So the value of my acceleration here is minus 7 meter per second squared. But do you know that if I gave you this kind of question, if I were to be the examiner, I gave you this kind of question, I asked you to find the deceleration, and you got this, I will only give you 98 over 100. Why? Because you have gotten the acceleration for me. The acceleration is minus 7 meter per second squared, but that's not the deceleration. The deceleration itself is the 7 meter per second squared. You don't have to put the minus there, because you already name it as deceleration. And like I wrote the other time, let me show you what I'm trying to talk about. I wrote it the other time that deceleration is minus a. So if deceleration is minus a, then I've gotten my a. So d will now be equal to minus, so what's my a? My a is minus 7. So that will be what? 7. So that's why my deceleration is 7 meter per second squared. So, but if it is the acceleration will be minus 7 meter per second squared. So we've done justice to that part of the question. So we've gotten the average retardation. Now to the last stage of the question, which is find the total distance covered throughout the journey. I would advise that you calm down to follow through with what I will do in this case, because it's challenging a little, but if you calm down, it will be a walk over. So now we need our graph again. we need our graph again. To find the total distance covered, like I said, if this had been a trapezium, it would have been very easy for us, because we must have heard one time or the other that the total distance covered in during a journey is simply the area of trapezium. If the velocity time graph is giving you a trapezium, just find the area of trapezium. And what's the area of trapezium? 1/2 into a plus b times I. But now, what's the name of this shape? Is it a trapezium? Are we still going to use 1/2 into bracket a plus b times I? This is where the problem comes in. But what they have said is actually going to be very useful here. What made us find the area of a trapezium? And that gives us the total distance covered. This same thing is what we are going to be applying here. I would say, since we have split the stages of motion into different things, we have the first stage, we have the second stage, the third and the fourth stage. I'm telling you, since this is a uniformly accelerated motion, each stages of the motion will give you a plane shape that you know. Let's test that out. Because it's a what? Uniformly accelerated motion. Let's see that. For the first stage, if you look at it very well, trace it out. This looks like something. What plane shape is that? That's a triangle. In fact, it's a right angle triangle. That's the first stage. Let's analyze the second stage of the motion. Look at it. By the time you trace this out, okay, perhaps I should even trace the stages of motion out. If you look at this very well, for this first stage, I have something of this nature. This is a triangle. For the second stage of the motion, I have this. I have something of this nature. What is this? This is a trapezium. And for this third stage of the motion, I have a rectangle. This is the first, second, and this is the third. And the fourth stage is simply a triangle as well. Now, this is very wonderful, meaning that all the stages of motion they are giving us a plane shape. The first one gave us triangle, the second one we have trapezium, the third one we have a rectangle, and the last one we have a triangle again. So what we just have to deal with now is, can you find the area of this plane shape? If yes, then to find the total distance covered throughout the journey is no longer a problem. All you have to do is find the area of each plane shape, and after you have done that, then sum everything together, then we'll be fine. Now, for the first stage, now we need to get some things out here. Now, what's the distance from here to here? What is the value of here to here? Mind you, in this situation, normally when we are dealing with plane shapes, it's always like our base, if our base is in meters, our height will also be in meters. Whatever we are dealing with, all the sides will be in the same unit. But in this case, they will be different. The difference is that if you look at my base for the triangle here, is anything I find at the base here is for the time. And anything that I find as an height here is for the velocity. And this is actually proving another point. From motion, generally we know that velocity or speed equals distance over time. What does this imply? This implies that S equals to what? Vt. And this distance is the product of velocity and time. And what does area do? Area combines what? Area simply multiplies the dimensions of a plane shape. That is, if the dimension of a plane shape is length and breadth, then the area will be length times breadth. If you have base and height, the area will simply be base times height. You can have maybe 1/2 there. That one is a constant. But the major thing you have there is base times height. If you look at that of the trapezium too, we had two sides and multiplied by the height. So in this situation now, what will be combining together is the time times velocity as we are computing the area. So for the first case, let's go. The time, which is the range from here to here, is 30, and for the height we'll have 240. If you come to this trapezium, from this place to this place, which is from here to here, if you mark that out, we have this place is also 240. So perhaps I should do it one by one so that we can see it clearly. Now, so let's find the area of this first. So to find the area of this, we just have half base times height, and that will be 1/2 multiplied by, what's our base? Our base is 30 and our height is 240. If you do this very well, 2 will be 120, and so that will be 3,600 meters. So we can take note of this. This is the distance covered in the first video, at least from here to here. The distance covered is 3,600 meters. Now let's take the next stage into consideration. We have this stage. So if we look at it very well, from here to here, that's between 30 and 50. What's the change in time there? That's 20 seconds. So you can say this place is 20. Now from here to here, if you trace that to this place, that's 140. So this place will be 140. And from this place to this place, which is from here to here, that will give 240. And if you trace it out so that it will look like a trapezoid like you do, this and this are parallel. So, and they are stopping at the same, they start at the same point and stop at the same point, so they will have the same length. So this is 20 as well. So we can see from here that since the area formula for finding the area of the trapezium is 1/2 into A plus B times the height. This is just a slanted trapezium. So let me draw it the normal way we used to know. So our trapezium is something of this nature. Something of this nature. There we have our height to be 20. This longer part from here to here is 240, and this shorter part is the is 140. So we have all we need. So our A is 140, our B, which is the longest side, is 240, and our height is 20. So all we just need to do is to slot it in now. So we have 1/2 A plus B, that's 140 plus 240, then times the height. The height is 20. So if we do this very well, the one in the bracket will be summed up to be 380. And because 2 can go in 20 to give us 10, so we have 380 multiplied by 10, so we have 3,800 meters. So we've gotten the distance covered in the second stage of the motion. So don't forget, we got 3,600 for the first stage, and we have gotten 3,800 for the second stage. Permit me to just write these two values because I'm going to rub these ones up now to get the remaining two stages. So for the first stage, we have 3,600. For the second stage, we have 3,800. Don't forget they are in meters, so I can rub this off now. So the third stage, by now, this shouldn't be straight. What we're doing here shouldn't be straight to you anymore. If you bring this shape out, that's just a rectangle, and if you look at the sides of this rectangle, the range of this line will be 60. 110 minus 50, that will be 60. And then if you trace it up, it stops at 140. So definitely this longer side will be 140. And this is one of the simplest of the plane shapes to find its area. The area is length times breadth. So what's the length here? The longer side, which is 140 times 60. And then, so what's 140 times 60? If you compute 140 times 60, I think I have my calculator here. 140 times 60, that will give us 8,000. 140 times 60, that will give us 8,400. So that will give us 8,400 meters. Now, that's the third stage of the motion. Now let's take the fourth stage now. The fourth stage, which is a triangle. the triangle from 110 to 130, that will be 20, and the height is still 140. So using our formula again, area is 1/2 base times height, so we have 1/2 times, what's the base? 20 times, what's the height? The height is 140, and if you compute that, this will be 10 times, that's 1400. So we've been able to compute the distance covered in the 4 stages of motion. And if all the entire motion comprised of 4 stages, and you're looking for the total distance covered throughout the journey, all you have to do is add the first stage, the second stage, with the third stage, and with the fourth stage. That will give you the total distance covered. So the total distance covered, I'll move up now. I don't think I need to rub this. Okay, let me go to 2. So the total distance covered, oh, we didn't write that. The third stage we have 8,400 meters, and the final stage, which is the fourth stage, we add 1,400 meters. So total distance covered will be equal to 3,600 plus 3,800 plus 8,400 plus 1,400, and if we add everything here, we have 8,400 plus 3,600 plus 1,400 plus 3,800. So everything here sum up to be 17,200 meters. So the total distance covered throughout the journey is 17,200. As before I proceed, as an assignment for you, try and do this. Let the stages of motion, let's blend the third and the fourth stage together, because if you look at the third and the fourth stage, it can actually be combined together to give us a trapezium. So I would like you to combine it together, see whether if you add the 3 together, it will still give us 17,200. Of course, me, I've done that as an assignment before coming here. It is actually going to give it to me, but it is left for you to try. So let's erase this part. This is a trapezium. So try it out, the first stage. Of course, you don't need to compute the 2 again. This is the only thing you have to do. Do it and add it up and see if it's actually going to give you this exact distance. So this is the total distance covered, and I think by doing this we have done justice to everything that the question wants us to do. So thank you very much.